Hello everyone. Today, I want to talk about one of the most powerful tools in mathematical analysis. The Taylor series. Think about it. In math and science, we constantly run into functions that are, frankly, unwieldy. Functions like sines, logs, or exponentials are incredibly hard to calculate by hand. Have you ever wondered how your calculator actually finds the value of sine of 0.5? It doesn't have an infinite table stored in its memory. Instead, it uses a process to turn these complex curves into simple arithmetic, just addition and multiplication. This is where the Taylor series comes in. Its core objective is simple: to represent any smooth, differentiable function near a specific point as a simple polynomial. By doing this, we can radically simplify the complexity of the world around us. The theoretical foundation. So, how does it work? The basic idea is that we can perfectly describe a function f of x if we know its value, and the value of all its derivatives, at just one single point, which we call the expansion point or the center, labeled a. Take a look at the general formula. F of x equals sum of n equals 0 to infinity of fn of a divided by n faculty times in parentheses x minus a to the power of n. To break this down, fn of a represents the nth derivative at our point a. N exclamation mark is the factorial, which scales our terms. And x minus a is simply the distance from our starting point. Quick side note, if this breakdown is helping you clear up the calculus fog, please give this video a like. It helps other students find this content, and you can subscribe to join our community for more math made simple. The sculptor analogy. To visualize this, imagine a sculptor carving a statue. At the zeroth order, we only know one point. Our approximation is just a flat, horizontal line. At the first order, we add the slope, the first derivative. Now, we have a tangent line. By the second order, we factor in the curvature. Our line becomes a parabola that starts to hug the original curve. The more derivatives we include, the higher the order, the more precisely our polynomial follows the actual function. Why do we need this? You might ask, why go through all this trouble? First, physics. We often use something called linearization. For example, with a swinging pendulum, the math involves sine of phi. For small angles, we use a Taylor approximation where sine of phi is approximately equal to phi. Suddenly, a nightmare differential equation becomes a simple, solvable system. Second, computer science. Computers can't draw a sine wave, they only know how to add and multiply. Taylor polynomials let software calculate complex functions to whatever precision we need. Finally, it's a lifesaver for determining limits. Sometimes Taylor expansion is much faster than L'Hopital's rule for seeing exactly where a fraction is heading. A concrete example, ln x. Let's put this into practice. We're going to expand f of x equals ln of x around the point a equals 1. Step 1 is finding the derivatives. Our function at 1 is 0. The first derivative gives us 1. The second gives us minus 1, the third gives us 2, and the fourth gives us minus 6. Step 2 and 3, we plug these into our formula and simplify. What we end up with is this beautiful, alternating polynomial. T4 of x equals x minus 1 minus 1/2 times in parentheses x minus 1 to the power of 2 plus 1/3 times in parentheses x minus 1 to the power of 3 minus 1/4 times in parentheses x minus 1 to the power of 4. Step 4, verification. If we use this to find ln 1.1, our polynomial gives us 0.095308. The exact value? 0.095310, we are already accurate to 5 decimal places just with a few terms. The catch: convergence and limits. However, we have to remember, a Taylor polynomial is a local approximation. This brings us to the radius of convergence. Our ln of x series, for instance, only works between 0 and 2. If you try to calculate ln of 500 using this center point, the result will completely diverge, it'll be totally wrong. To prove exactly how accurate we are, we use the Lagrange remainder. This term represents the error left over when we stop the infinite series. If that remainder goes to 0 as we add more terms, our approximation becomes the function itself. Conclusion. In conclusion, the Taylor series is the bridge between the complex world of calculus and the simple world of algebra. It shows us that by closely observing a single moment, that point A, and its derivatives, we can predict where a process is going. Whether it's in quantum physics, engineering a bridge, or the graphics chip in your phone, Taylor series are working in the background to keep the world calculable. Thanks for sticking around until the end. If you found this helpful, please like, subscribe, and share this with anyone currently battling calculus. See you in the next one.